Hi, I'm Chandrasekhar Ramanathan. I'm a professor at Dartmouth College, and today I've been challenged to explain a topic at 5 levels of difficulty. So what is quantum sensing? We're looking at the rules of the microscopic world, which is quantum mechanics, and using those tools to help us build the ultimate sensors, which means that they're as precise and as accurate as the laws of physics allows. What's your name?
Namina.
Our topic today is quantum sensing. So quantum is about the study of stuff that's really, really, really small. And sensing is about measuring. So the word sensing comes from kind of like our senses. So do you know what your 5 senses are?
Seeing, hearing, tasting, and smelling.
Mm-hmm.
Yeah, touch.
Touch, exactly. So it's kind of really important for us to be able to have these senses so we know what's happening in the world around us, right? What we do in quantum sensing is we're trying to measure things that can be hard to see. Let me show you. Can you see inside it with your eyes?
No, I don't
No?
think so.
Okay. Can you bounce it for me?
Mm-hmm.
Do you know what makes it bounce?
I think, inside of it, it's foam that's fluffy. But my second answer is I think it's very soft.
That's a great description. Can we cut one open and see what it looks like?
Yeah.
I think that's a good idea. Here's a ball that's been cut straight in half. Can you look inside it?
It's hard.
It is. Or what gives it a certain texture?
It's like the texture of the top of a crayon.
But you were right that it was like foam. It would be really cool if we could see inside the ball without cutting it open, right?
But you could use a magnifying glass and then look at the ball.
But with the magnifying glass, you'd only be able to see it right near the surface, right? You won't be able to see into the middle. If you had the right tools, you could start to think about ways to look inside the ball without cutting it open. That would then, you'd still have your ball. We could still play with it.
Yeah, it would be cool if we use something like an x-ray. We built an x-ray that was only made for balls. And you could see everything inside it, every single detail. You could zoom in and out in it, and you could draw it, print it out.
That's exactly the type of thing that we're doing. We're sensing is we're trying to measure what's inside. We're trying and do it without destroying the ball.
Yeah.
For example, we want to go inside, let's say, the human body and see what's happening. Sometimes we can look under the surface of the earth and see what's underneath it. We can make really, really precise clocks that will tell us, that can measure time really, really accurately. And we can make very, very fine measurements that will tell us about the rules of science and how the world works around us. But we need to build better tools that allow us to do that. Our topic today is going to be quantum sensing. Have you ever heard of it before?
No.
No. Okay, what do you think it might mean? If you just break down the words.
Something on a very small scale because of the word quantum. The sensing part, I'm not sure.
So sensing is really just about measuring stuff.
Okay.
And at some level, there's a different set of rules that seem to come into play. Because you can have particles at very microscopic scales seem to do really strange things. But one of the quests of quantum sensing is to harvest some of these unique properties at the microscale. We are really interested in quantum sensors because we think they can give us the ultimate limit of sensitivity. So they're really, really sensitive to small changes. But they're also going to be really reliable. Every time I make the measurement, I'll always get the same results.
Okay. Measurements on what kinds of things?
Could be almost anything you want. Have you ever broken a bone?
Well, I fractured something, though.
Okay. Do you remember having an x-ray?
Yeah, x-ray, and I have had a few MRIs before,
You've
too.
had a few MRIs before. And so both of those are in some ways a form of sensing. And they rely on different types of sensing. Do you know what this image is?
Maybe an MRI?
Exactly.
Yeah.
Do you know how an MRI works?
No, I don't. And I feel like I should because I've gotten them millions of times.
And what the MRI scanner is doing is it's measuring the signal from all the water molecules that are present, and specifically the hydrogen atom. In our bodies, we have these hydrogen atoms that are essentially spinning around magnetic fields all the time, and we just don't know them. So in some sense, you've already used a quantum sensor.
Yeah. So are MRIs essentially more detailed x-rays?
They're not. So they're giving us different types of information.
Okay.
So this is an X-ray, you don't see any of the soft tissue. The X-ray gave us information about the bone.
Yeah.
Whereas the MRI is giving us information about things like the softer tissues.
Yeah.
And in fact, we don't see the bone very well in the MRI. So there are slightly different reasons why you would choose the two different things. Suppose I could get a higher resolution. What do you think I would be able to see?
The different atoms and the structures of the particles. Yeah.
Start to see the different cells and then the different chemicals in the cells. If you look at the MRI images, you can see that they give you the broad features of what the tissue looks like. But if you want to zoom in a little bit more and see what's actually happening inside a tissue or inside a cell, and you need a different type of sensor that's going to be more sensitive, and for something like that, you're going to need a quantum sensor.
Are there different types of quantum sensors for different things?
So one of the quantum sensors that's related to the work that I do is based on these defects that are called nitrogen vacancy sensors in diamond. And people actually now make nanodiamonds that they can try to put inside the human body to look at the chemistry inside the cell.
So is that used for drug trials and when testing out new treatments?
We can do it on tissues right now or on the surface, but we can't actually do it inside the body. So right now we're struggling to figure out in which scenarios can we use this to get better information and when can we not do it.
Are there any other quantum sensors at the moment that aren't in the developmental stage anymore that we are using?
So there are quantum sensors that are sold for very specific applications. One of them is a magnetometer, and those can be really, really sensitive to measure small variations in magnetic fields. They're trying to develop sensors that are gravitational sensors. Right now we have no way of probing what's under the ground without digging into the ground.
You talked about a sensor measuring magnetic fields. What does that help us learn? What is that good for?
Well, if I want to navigate and I know what the structure of the Earth's magnetic fields are, in some ways that's how birds navigate.
Oh,
so the avian compass, in fact, people think of that as a quantum sensor.
Okay, so they've
it's
got
a
like
biological
built-in
quantum sensor.
Yeah.
They have a built-in sensor. And one of the ideas is that they're using quantum phenomena to figure out what the direction of the Earth's magnetic field is. That's why they're able to be, homing pigeons are able to come back to their original location.
Oh, that's cool.
Yeah. What year are you in?
I'm a senior. I'm studying physics right now.
Cool. What do you think of when you hear the words quantum sensing?
I think that using some sort of quantum computing to sense some quantum level molecules or particles, like interactions and stuff, maybe.
It is exactly using quantum phenomena to sense and measure things. And the idea is that if I can harness quantum phenomena and I can push the limits that are possible, I can get something that's ultimately more precise and potentially more accurate over time, too.
How is it more precise?
We believe quantum mechanics tells us what the true laws of physics are. And so a quantum sensor in that sense would reach the limits of what's attainable.
It would be the top tier.
It would be the top tier.
What are you doing? Like what are you
So I study spins, and so spins are one of the platforms that people have suggested is a useful platform for building quantum technologies. And I study spins in the solid state. And one of the platforms I work on is nitrogen vacancy centers in diamond, which is a really nice platform because the spins show their quantum properties even at room temperature.
So are you studying the spins of the electrons?
So in some sense, the phenomena we're studying is nuclear magnetic resonance or electron spin resonance, which is a very similar phenomena, but uses the spin of the electron rather than the spin of the nuclei.
So you mentioned the diamonds that are used to create the sensors.
Right.
So how long does it take to make a sensor and to make that diamond? Is that created? Do you put energy into it, or
so you can implant nitrogen into a diamond and then you bombard it with electrons to create the vacancies, and then you heat it up and anneal it, and then you get these nitrogen vacancy centers in your system. So you mentioned quantum computing earlier. So have you heard of the idea of superposition?
Yeah.
So that's in some ways the key to both quantum sensing as well as quantum computing. It's the idea that you can take a system and put it in a superposition of two states. Normally we think of classically a bit can be a 0 or a 1. So switch is either on or off. Whereas in a quantum system, it can be in what's called a superposition. So it can be in partially on and partially off. But one of the challenges with quantum systems is that these superpositions are really hard to maintain because we don't see superpositions in the world around us. In a quantum computer, you try really hard to isolate everything so that you can maintain this quantum property. And the fact that it's actually going to lose its quantum properties as it interacts with the world also makes it a great sensor. Because now you're using that fact that it's interacting with the world to say, wait, it's sensing something.
Okay. So it's like using like the quantum computer would be kind of like the base level, and then like you take it out into the world and see how like it differs?
So rather than trying to build a lot of complex algorithms and gates with it, what you do is you take these quantum bits and you take them out into the world and say, what do you see? What are you sensitive to? So you can use an idea called entanglement to make an even more sensitive quantum sensor, but it's even more fragile. So there's always this trade-off between being super fragile and being super sensitive.
How does
at the same time.
entanglement work into it?
So entanglement is the idea that two particles are correlated. They're essentially in the same quantum state so that you can't disturb one particle without disturbing the second particle. And so if I have a large number of quantum sensors that are entangled, then they're all going to interact much more strongly than if I just had one of them interact at a time.
Okay.
And so that gives you a boost in sensitivity when
And
you
so
have
it's
an
more
entangled
precise
sensor.
if you
It's
have
more
entangled.
precise, absolutely.
Okay. Is an atomic clock a quantum sensor?
In some ways it is. And atomic clocks are remarkable devices. And being able to measure time that precisely, it has really important consequences. In fact, our whole GPS system is based on the accuracy of atomic clocks. So a set of satellites, each of which has an atomic clock on board. And they send out a timestamp. And so once it gets a signal from 3 different satellites, it can triangulate and figure out exactly where you are. Now, if you could make those clocks even more precise, you could actually accurately position where you are even more accurately.
Okay, that's really cool.
So some ways, when atomic clocks were designed and built, we didn't necessarily think of GPS, but technology often works that way, is that there are new discoveries and then someone else comes along and says, hey, this is a great tool for some other application. So what drew you into quantum computing?
I think what got me into material science was actually making semiconductors for
Okay.
solar panels. Then that drew me into new types of technology that use semiconductors. The one that's very popular now is quantum computing. And what about you? What got you interested in quantum sensing?
I started out doing magnetic resonance, study things like bone and biomedical magnetic resonance. Ended up playing with spins for a long time, and the physics of spins just fascinated me.
So what do you think is a big difference between imaging large biological objects versus sensing very small quantum objects, I guess?
In a way, it's part of the same continuum. What you're doing is changing the technological platform, and you're actually able to probe it more sensitively. The resolution you're able to get is much higher. So you can see smaller signals in a much smaller volume.
How is the resolution higher?
So it's because the nitrogen vacancy center is a single defect, so you can actually see a single electron. In normal magnetic resonance, you don't have the sensitivity.
In order to be sensitive to like a single electron, do you have to be really close to it?
You have to be close to it. You can detect it optically. Because if we tried to detect the magnetic moment of the electron, we wouldn't be able to do that because there the energy is too low compared to thermal energies. But what the diamond system gives you is a natural upconversion energy. So you can couple into an optical photon, which is then much easier to detect a single optical photon than it is to detect a microwave.
Okay, I see.
Yep. And that's why you're able to do it at room temperature as well.
What are some of the challenges you've faced when trying to do quantum sensing with this platform?
One of the key challenges, I think, for any quantum technology is really understanding what limits your coherence times. And then the next question that comes up often is, how do we make this better? So if I take a single qubit or a single spin, there's a certain limit to its sensitivity. But if I can take entangled spins, in principle, I could make the system much more sensitive. But it usually comes at a cost, because when I entangle something, it's much more sensitive to decoherence as well.
In a similar way, but maybe even in the opposite way, where we want to figure out how to be as resilient from noise and all the kinds of noise sources.
Exactly.
Okay.
What are you studying?
I'm studying superconducting qubits that use hybrid semiconductor-superconductor structures.
Mm-hmm. Your semiconductors, are you introducing new noise sources potentially that might affect the coherence times?
Yeah. So the big one is charge noise, because I guess a lot of the superconducting qubits, they have made them in such a way that
Right.
they're insensitive to charge.
Exactly. So when you think of noise, in what way is a noise bad for your system?
I usually think of it like, well, we work with quantum systems.
Yeah.
And those are very sensitive to fluctuations. I
Yeah.
guess any fluctuations can kick your quantum system either out of the state that it's in to another state.
I think, as you said, anything that interferes with my signal is noise, but it can come from different sources. In some ways, the operation of the quantum system itself, as it's sensitive to different physical phenomena, The ones that I don't like, I call noise. The ones I do like, I call signal. And that's an artificial definition that I'm making when I choose to build a sensor. One of the challenges we have is we're trying to figure out, if I want to control it, where is it coming from? I remember we had experiments running in our lab one day, and we were running these experiments at about 100 megahertz. All of a sudden, we saw these big spikes coming in, and we realized we're picking up the local FM stations. And that was a source of noise. It's completely random, but it is still there. And then the other form is very much what is intrinsically within your experiment itself, because some of the materials that you have defects that are coupling into your sensor, into your quantum system, and are also producing noise.
But yeah, the interesting stuff really is where you're picking up the quantum noise from intrinsically from whatever.
Right. It could give you information if you read it out about what's happening, or you have to find smart ways to suppress it so that you can focus on what you really do care about.
So what are the kind of noise and fluctuations that you're worried about?
So one of the things that we're interested in is looking at, suppose I want to build an entangled quantum sensor. When I put a number of spins together, in addition to being sensitive to an external field, they're sensitive to each other. And they start talking to each other. You don't just see the external spins, you see the fluctuations of all the other spins in your system. So what you want to do is make sure that they don't interact with each other, but they still stay sensitive to everything else. And there you could think about the local interactions, the magnetic interactions between the spins as a form of noise. In some ways, it's interfering with what you want to measure, which is the magnetic field outside the sample. So our topic today is quantum sensing, which you're an expert on. Can you recap for us in your perspective? What is quantum sensing?
That's $1 million or maybe $1 billion question.
Exactly.
Yeah. I think a lot of people in the field have different definitions for it.
Absolutely. What would you want to be like the smoking gun of a quantum sensor?
Depends on who I'm talking to,
Right.
Trying to talk to students and get them excited, or, try to talk about the elements of quantum mechanics. I think maybe we could agree that, things that use superposition have a certain degree of quantum mechanics, quantumness involved. Maybe they should be using elements of quantum computation. So I don't have a strong view on it, but I do think it's an interesting question.
I would tend to agree that I think, in some sense, anything that uses superposition could be a quantum sensor, but then spectroscopy uses superpositions and has been around for 60, 70 years. I think what excites me most now is the idea that can we push the boundaries of how sensitive one can make this technique, how improving sensitivity, specificity, what are the limits, and as we define it better, are there fundamental physical limits?
That's where the excitement lies, is when we really start to leverage having, access to individual quantum degrees of freedom, whether that's a single photon or a single spin. And in principle, then you could also imagine entangling it and, doing some quantum computations on it in order to make it an even better sensor.
So do you think there's a maximum number of spins you can have if I think about a single NV as a register?
Right. I mean, people have thought about this. It's an interesting question. You can think about, you have the electron and it's surrounded by some nuclei, and you could change the density of those nuclei. And so if it's a lot more dense, then you have a lot more that are strongly coupled, but you also have a lot more noise.
Right.
But I don't know that there's necessarily a limit. I mean, it's been keeps expanding. I mean, I think that there are some groups that are able to identify 30, 40 individual nuclear spins around a single electron and control 10 or 15 of them.
So do you think you can integrate multiple NV sensors or multiple optical sensors? So are there ways in which you can overcome this question of there's a spot size and that limits how many NVs I can pack into a certain region?
That's another great question. A couple of groups actually that are working on trying to read out the spin state of NV centers electrically instead of optically. If you could do that, then you could pack a whole lot more into a smaller space using tiny electrodes, and you could possibly have them spaced at nanometer scales instead of at micron scales. And I think the application there is clearly sensing. Right.
Do you think they'd retain their coherence times if you packed them in?
Yeah, what's limiting the coherence is really local, right? Nanometer scale. But it happens to be that most of the time when we try to read them out with light, well, then the trouble is that the diffraction limit of light is, hundreds of nanometers. And so then we need them to be apart. But, if you have two NV centers that are more than a couple tens of nanometers away from each other, they just don't talk to each
isolated.
other. Yeah. So from that point of view, the technology could be really dense, right? Which is why, some, companies or groups are trying to make quantum computers based on spins in semiconductors, because they could be really densely integrated using modern technology. But the question for a sensor is, as you say, how do you address it? How do you initialize it? How do you read it out? And is optics the best way to go? And it may not be. If we think about quantum sensing in particular, it really involves understanding materials, solid-state materials, chemicals, chemistry, biology, engineering, electrical engineering, optics, photonics. I mean, so many different areas. I think that that's one of the most exciting things about that is the degree to which it's engaging a much larger cross-section of scientists. They're the ones that I think are going to come up with the breakthroughs of saying, oh, wait, I could design this molecule to do this thing. And that, I think, is going to make real breakthroughs in the next 10 years, is the fact that we're just having this much larger group of scientists.
People bring in very different perspectives into what used to be a very niche field. I remember physics, you'd only talk to people in your subfield, and now we're picking up the phone and talking to people in the different departments, completely different areas, and we're forced to learn different languages. The quantum world is essentially the world of the very small, but one of the quests of quantum sensing is to harvest some of these unique properties at the microscale. And with these tools, we will be able to have new technologies and new measurements that we are unable to make today.